Hey, and here we are with example 2 of lesson 2 of related rates. As promised, this problem will require us to approach it with a bit of a geometric perspective, meaning we're going to have to know, in this particular case, what the formula for the volume of a cone is. So here's the question. Sand pouring from a conveyor belt forms a conical pile, a conical meaning cone-like, the radius of which is 3/4 of the height. If the sand is piling up at a constant rate of half a cubic meter per minute, at what rate is the height of the pile growing 3 minutes after the pouring starts? Okay, so let's start with a diagram. Okay, so this is sort of how I envision it, right? You're pouring sand onto a spot, and as the sand is coming off of the conveyor belt, it's forming this conical pile, right? And so maybe it starts out small like this, and then it grows and it grows and it grows and it grows until it reaches, some shape like that. Okay, so this is theory. It's not. It's not going to be a perfect cone, but it'll be cone-like in shape. And so we're going to model this with the volume of a cone formula. Okay, which by the way is coming up. But first, let's work with the diagram a little bit more here. So the radius is 3/4 of the height. Okay, so let's go with this then. If I take, say, I guess I'll have to do this. Let's go with, this might be a little bit thick. Yeah, it's a little bit too thick. Let's try, I guess we'll just go with this. So the height there is going to be equal to h. And the radius, so this piece right here, is going to be 3/4 h. Okay, so then that's good. So that's how those two pieces relate to each other. Now the volume of a cone, you may recall, is 1/3 pi r squared h. So 1/3 the volume of the cylinder with the exact same height and radius. Okay, so that's our equation that relates, well actually it relates three quantities together, the radius and the height and the volume. And what we want to try to do with this equation before we do any sort of differentiation is we want to make sure that we've got the correct two quantities related to each other, right? It's just adding a level of complexity if we have that third piece in there, right? It's kind of like going on a date, but then having, your little brother tag along as well. It's just kind of awkward. Okay, so let's see. If I go V is equal to 1/3 pi, and r is, let's say, 3/4 h squared, right? So I made that substitution because this technically is r, but r really doesn't have anything to do with it, right? It's asking for the rate of the height of the pile, right? At what rate is the height of the pile growing? And it does give us the rate that the volume is increasing. So volume, yes. Height, yes. Nowhere does it mention anything about the rate of the radius increasing. So out with the radius, in with the height, and don't forget this h out here. And so when I expand this, I end up with something like 1/3 pi 9/16 h squared h. Okay, and simplifying that, I'll end up with, let's see, 3 goes into itself once, 3 goes into 9 3 times. So I think I'm at 3 pi over 16 h cubed. Okay, so that's the formula that relates the volume of this cone to its height. Okay, and it's not going to be the same equation for every cone, right? It's specific to this cone or any cone that actually has a radius that is equal to 3/4 of the height. Okay, so I boxed that off, but that's not my answer, so I'm just going to unbox this. So I've got the equation. Now I'm going to go to the derivative, or the related rates equation. So dv dt is equal to, the 3 comes in front, and I get 9 pi over 16 h squared times, by chain rule, dh dt. Okay, and so I have dv dt, that's the 1 point, or so that's the half, and then h, see, I don't know what the h is. It says after 3 minutes. So at what rate is the height of the pile growing at 3 minutes after the pouring starts? Okay, so then what we're going to do here is make use of this volume formula, or this volume rate, which says we've got half a cubic meter every minute. So after 3 minutes, we will have half times 3 minutes, which equals 1.5 cubic meters. Okay, so I'm making use of, maybe we can't see this right now very clearly because of the box, but I'm making use of this piece of information that says that the volume is being increased, is being added to the pile at a rate of half a cubic meter per minute. And after 3 minutes, that would be 1.5 cubic meters. So going back to this formula, if I sub in 1.5 cubic meters, I should be able to get the equivalent H. So we'll need a bit more space to evaluate the H. So 16 times 1.5, that will be 24, is equal to 3 pi h cubed. This would end up being 24 divided by 3 is 8, divided by pi equals h cubed. H is equal to the cube root of 8 over pi, which I believe is going to be equal to about 1.37. So now that I've got the height after 3 minutes, I can go back to the related rates equation and sub in h, which in this case is 1.37 squared, times dh dt, which is what we're after. I can also sub in dv dt, which is half a cubic meter, right, per minute. Okay, and then now what we're going to do is isolate dh dt. So let's see if we can do that in one fell swoop. So I'll end up with, let's see, so dh dt would be equal to, the half stays on this side if I'm going to isolate the dh dt, so I've still got half. I'm going to multiply the 16 to both sides. I'm going to divide both sides by 9 pi. Okay, so I've taken care of this fraction, and then I'm going to divide both sides by 1.37 squared. Okay, and the final answer will be, by my calculation, 0.152. Okay, and that would be meters per minute. Okay, and where I get the units from is, of course, from here, right? We're measuring the volume in terms of cubic meters, and so the height is going to be increasing by meters, and the units of time is minutes, so meters per minute.